Single sideband is a ham radio for boats. We use what's called the upper sideband to create a signal that is transmitted globally because it bounces off the ionosphere. And so it's a very powerful radio. It uses a lot of juice, but it's the cheapest way to have global communications. Once it's installed, you can pretty much talk to anywhere on the planet and you don't have to pay per minute. If you have a satellite dome, you can talk anywhere on the planet and you got to pay per minute. So these are the sections we're going to be covering in here. We're just going to do a quick overview of single sideband versus VHF, and then we're going to talk about installation considerations for single sideband, the ground plane, the antenna testing, and also the DSC function, which we already covered in the DSC section, the frequencies that you use, but we'll touch on that again. So this is just a comparison matrix to compare the VHF and single sideband. So the frequency is different. Obviously, we use 2 to 30 megahertz on single sideband. We use the even numbers. Ham radio uses the odd numbers. So we use 2, 4, 6, 8, 10 megahertz. Ham uses 3, 6, 5, 7, 9 megahertz. And again, we use upper sideband as our modulation type. So the VHF radio transmits at 25 watts, a single sideband 150 watts. The 150 watt single sideband transmission forms a ground wave, which is about 150 miles, something like that. And so you got direct communication without counting on bouncing off the ionosphere. You can talk 100 to 150 miles with a single sideband using the ground wave. And so obviously the VHF is short range and the single sideband is long range, because in addition to the ground wave, the single sideband bounces off the ionosphere and bounces all the way around the planet. And there's a lot that goes into that in operating a single sideband. So if your customer thinks they can buy a single sideband and have global communications without learning any new tricks, wrong. They're going to have to learn a bunch of new tricks. They're going to probably have to read some books and keep them with them. So this thing typically is, well, they can be 12 or 24 volts, but this thing draws a very little bit of current, say 6 amps. This one, 30 amps is typical. And this is really true. This is usually like 4 or 5 amps. This is really, truly 30 amps. So the bottom line on this is one of the mistakes that a lot of people make in installing this thing is too skinny of a wire. Go look up how fat that wire has to be to deliver 30 amps, 15 feet across that boat from your battery supply to that single sideband radio. You're going to need at least a 6-gauge wire is my prediction. You're not going to do that with 10-2. So just keep in mind that this thing really does draw a lot of juice. It doesn't just think, it doesn't act like it. Like an autopilot, for instance. You might say, oh, that autopilot draws 40 amps. Well, yeah, every now and then it does, but not very often. This thing often draws 30 amps. You don't need an antenna tuner. Here we need an antenna tuner. So the antenna is matched to the VHF just by the way it's made. Here we match the antenna to the single sideband using the antenna tuner. This thing makes the antenna look like a half-wave antenna to this guy, or at least a quarter wave. And you don't have to have a ship's radio license here, but you do for a single sideband. And by the way, if you're having a single sideband, you're also required to have a VHF. So you can't put a single sideband on the boat and not have a VHF. So that's just a comparison matrix. This is a really cool graphic. So we got our depending on here's our ground wave zone, so we can get straight to the boat through the ground wave. And then here's where we can't talk because it's outside of the ground wave and it's inside of the first bounce. So this is the ionosphere. It bounces off the ionosphere in a specific way. So when it's daytime outside, the ionosphere is destroyed. and you can't bounce off of it anymore. So you have to bounce off of a dark part of the sky. So just because it's daytime here, that doesn't mean you can't bounce off of a dark part of the sky in Europe and come down in Asia. But anyway, that's why it's hard to operate this thing. You can't just pick up the thing and just choose any channel and start jabbering like you can on a VHF. You need to use the correct frequency, lower frequencies during the night and higher frequencies during the day. I'll double check that, it's coming up on a slide. But depending on the time of day, you have to choose the correct frequency. And that's the biggest trick. So this just shows what components are involved in a single sideband radio. You got your antenna, and this varies depending on what kind of boat it's on. You got a high voltage wire. This is called GTO wire, GTO 15 wire. It looks like a piece of coax, like a round white piece of coax, but if you strip it off, it's 10 gauge or something like that, 10 gauge wire inside, and then just super thick insulation. So it's high voltage wire. When this guy transmits, it transmits high voltage. So here is our ground plane. This is a grounding plate underneath the boat with a minimum 100 square feet, like the Dyna plate that's 6 inches by 18 inches, has an equivalent of 100 square feet. That would be the smallest one you'd want to put on there. And then this needs to be located physically close to the tuner and below it, and hooked up with a copper strap down to the plate. So this is all about surface area, and that copper strap is part of the antenna. All of this stuff is part of the antenna. The high voltage wire, the ground strap, the ground plate. This is half of the antenna, and this is the other half of the antenna. If you don't put a ground plate on this thing, you only got half an antenna, and it doesn't work at all. So if you have a crappy one, it'll work crappy. If you got a good one, it'll work good. So this coax coming from here, 50 ohm coax coming from the radio to the antenna tuner, that's a maximum 2 dB of loss on that cable, right? We got 3 dB loss in a VHF, but this is more stringent. Only 2 dB can be lost through this coax. And then in addition to the coax, we have the control wire connection. So this is a 4-pin, usually a 4-conductor wire, and it just goes from the transceiver box to the tuner. And so when you key the microphone here, and you're on 8 megahertz or whatever, and you key the microphone, it doesn't, the transmit light does not immediately light. You hear clickety click, 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 click for a second or so, and then the transmit light lights. So what it's doing is when you squeeze this mic, it sends a signal, hey, tune yourself to 8 megahertz. And clickety, click, 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 it throws a bunch of relays, it tunes itself to 8 megahertz. And then it sends back, okay, I'm tuned. And then, doop, it goes. Sorry. And then then the radio starts transmitting. So first the tuner action happens, then the radio starts transmitting. There's a tune button on here. You can just hit tune and clickety click, 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 it tunes. And then when you squeeze the mic, it immediately transmits. Otherwise, if you squeeze the mic, there's going to be a slight delay while the thing tunes, and then it'll say tuned and the transmit light will light. So here is our DSC watch antenna. So in addition to your transmit and receive antenna, this is the big bad boy that does the hard work. We're also always listening to the DSC channels. So this should be a general coverage antenna. A proper DSC watch antenna for a commercial vessel is, I think, 4 meters long, or 13 feet or whatever. But a lot of times on pleasure boats, we use like a Metz base-loaded whip, costs about $100. It's called a general purpose antenna. It's just like, it looks like the one that goes on the top of the sailboat mast. It's just got like a 3-foot whip on it and a little base load. And that covers all the frequencies you need to meet the requirement to have a DSC watch antenna. If it's a Solus vessel, you're going to want to use a Solus rated watch antenna that's going to be 4 meters long. So that's the watch antenna. So on the back here, we got a PL2 SO259 or whatever it's called, the jack for an antenna jack for the transmit and receive antenna, and another antenna jack for the DSC watch antenna. So there's two antenna jacks back there. And don't confuse them, because this one puts out 150 watts of hateful RF energy, and this antenna doesn't like being transmitted into. So watch out for that. And we still have a connection here to our RF ground. This is our, wing nut, our fat green wire that goes to all the other fat green wires that go in all the equipment. But this does not get a fat green wire. This only gets a connection to its counterpoise, no connection to RF ground. This is the counterpoise. This is not RF ground. This is a ground of sorts, but it's called a counterpoise, and just as much current flows through this wire as flows through that wire. So this is half of the antenna. So anyway, that's why we can't really call this a ground. It's more like it's a counterpoise is what it is. Anyway, maximum 2 dB loss on this coax. This is just the coaxial cable comparison guide or selection chart or whatever you want to call it. And we colorize this so that you can see that the RG8 and the LMR 400, these are the same diameter cables. But look at the loss characteristics we get with this RG. We've got 2.6 here, 1.6. And when you get up, this is in the 900 meg or 160 meg VHF range. When you get up in cell phone range, 900 meg, the RG really falls off a cliff at 6.5, whereas the LMR is still 3.9. And as you get up into the 1900, 1.9 gigahertz range, which is up in SATCOMs and cell phone range, now the RG8U is completely useless. It's 12 dB per 100 feet, and less than half of that here. So this really shines at high frequency. This LMR cable is super low loss. See, this is a 1/4 inch in diameter, and so is RG8X. But look at the difference in the loss characteristics. Not as big of a difference, but still a pretty good difference. And then this is the skinny coax. This is really crappy. This, look at how much loss you get at these high frequencies. This is totally unacceptable. I never use that type of cable. If I need skinny cable, here's some skinny cable. It's just slightly fatter, 1232s versus 1332s, but way, way, way better loss characteristics. If you're way up here, look at that. This is a third of that. So RG213 is some badass coax there, but not as badass as LMR. So if you're looking at coax, you need to decide what kind of coax you're going to use. Hopefully you've taken the NMEA class and you understand about coax losses. And so just use, for the single sideband radio, remember we're talking about, what happened here? What happened here? Did I skip a slide? Okay, I skipped a slide. Sorry about that. I'm going to go right back to this slide again because I've already talked about it. But this slide is a good, really useful slide for selecting coax, understanding coax. These are the main 6 coaxes you're going to see out there. There, of course, are LMR 600, LMR 1000. There's all kinds of RG59AU. There are other ones out there, but these are the 6 most common. And so because of that, this is a super useful matrix. So this is this post-installation check slide that I skipped. We were talking about this slide where I went through all these various components, the control cable, the coax. Here's the coax that can only have 2 dB of loss, our DSC watch antenna. I'm just trying to get us back on orientation so that I can go to this slide. And after you've installed the thing, you must have a VHF radio with DSC capabilities. You can't have an old VHF radio there. You got to have a ship's radio station license, 1 antenna for transmit and receive, and a separate antenna for a DSC watch antenna. Don't forget, this thing draws a ton of juice. and then a modem for single sideband email if you're going to use a modem. And there's an antenna tuner. I'm not sure what this slide's trying to say, but these are some of the things you have to make sure you did right. And there's your antenna selection guide. And then let's talk about antennas. The antenna requirement depends on the boat. Usually single sidebands end up on sailboats in the pleasure boat world, and we use a backstay as the antenna. I did a single sideband last year, or year before last, on a 185-foot Coast Guard cutter that was converted to a pleasure boat, and I used a 10-meter freestanding antenna for that. It cost about $4,000, and it was like 5 or 6 inches in diameter at the bottom with a giant 12-inch flange on it that bolted through the deck. But a freestanding antenna, unsupported, 10 meters long, which is 30 feet for those of you who don't know. Here's a seat of the pants method to find out how long a quarter wavelength of the antenna is. Do 234 divided by its frequency in megahertz. So 234 divided by equals 58 feet. That's the quarter wavelength for 4 megahertz, 58 feet. So 2 megahertz is even longer, double that. And so this is the way you can find quarter wavelength seat of the pants method. So don't forget the antenna starts at the coupler and goes down to up the GTO wire is also part of the antenna, and so is the strap and the ground plate. So we're going to look at this GTO wire. We can get these freestanding antennas. Yeah, they're available. They cost a ton of money. These backstays, sailboats use these guys. And the idea here is our high voltage wire right here. And we want to stand this off at least 3 inches from metal. So after this high voltage wire comes out of the antenna tuner, and it's going up to the antenna element itself, which is an insulated portion of this steel cable, on the way from the tuner to the antenna, it cannot come within 3 inches of metal. So when you drill through the deck down below here, you're not going to want to drill right next to the stanchion and then tie the wire to the stanchion. You're going to want to drill 3 or 4 inches away from that stanchion and then stand the wire off away from the stanchion. Don't tie it straight to the stanchion. You're going to shunt the RF power to the stanchion and then to the water. So don't do that. So with the for wire antennas on sailboats, we use a backstay, a split backstay, or there's even a catch rig you can do. And this antenna insulator has to be 7 feet above the deck. If you got an exposed bare wire antenna like this, and somebody reaches up and grabs that because a big wave came by and they didn't want to fall overboard, so they reached up and grabbed that metal cable up there, and at the same time you squeeze the microphone and started talking in your single sideband radio, he will get an RF burn that's going to take 6 months to a year to heal. It burns from the inside out. It starts in the center of your skin and starts burning towards the outside, and that's not a happy kind of burn to get. If anyone's ever had an RF burn, it's not cool. So remember that when you squeeze that microphone, nothing happens. When you start talking, a whole bunch of voltage goes through this high voltage wire, and you've got a hazard to humans. The single sideband suppressed carrier, right? We only use the upper sideband. We don't put out that carrier. All we put out is the sideband. What that means is when you squeeze the mic, nothing happens until you start talking. Then the radio starts putting out. On a VHF radio, when you squeeze the mic, you're putting out full carrier wave at 25 watts, and you're just modulating that carrier back and forth as you talk. With a single sideband, there is no transmission until there's modulation, because what you're transmitting is only the modulation, not the carrier. You're only transmitting the modulated part of that carrier. So the antenna tuner is an impedance matching device, and it can any piece of metal can act as an antenna. And if you hook the antenna tuner to it, it's going to make that piece of metal look like a quarter wave antenna. but you have to have this counterpoise for this thing to work. 2 dB loss, separate DC watch antenna. So that the antenna tuner performs a very important task. You don't have to have a perfect antenna if you have a really good antenna tuner. You'll never damage your radio if you have an antenna tuner hooked to it. At least not because of a defective antenna. You may damage it because you run low voltage to it or something, but anyway, this is just the different types of antennas. You always have to have a ground on all of them. You always have to have 2 dB of loss, and you always have to have a separate DSC watch antenna. That's for all of them. So this is showing the backstay antenna where we come up through the deck. Our high voltage wire is here. We make sure that it's stood off of that backstay until we get at least 7 feet above the deck. Then we can hook it here. We want this insulator 7 feet above the deck, remember? So they can reach over and grab this one, no problem. And this GTO wire, allegedly they can grab that too, because that's why the insulation is so thick, it's safe. But once you get up here, you've stripped this thing off and clamped it on there with a hose clamp and some dielectric grease here. This part right here is hazard to humans. So we don't want to have that within 7 feet of the deck. So this insulator is 7 feet above the deck, and then this insulator is at least 3 feet from the mast. So 7 feet above deck for this insulator, and 3 feet down the cable from the for this insulator. So what we've done here is we've insulated this section of the backstay, and this becomes our antenna element right here. So the GTO wire comes, you strip it back about 3 times as much as you would for a butt connector, fold it back and forth a couple of times, goop it with dielectric grease and hose clamp it on there, and then tape the hell out of it. And then make the customer aware that that may have to be opened and retaped every year or two. If you have a split backstay, you're going to need 3 insulators. You can't just put 1 insulator here and 1 here, because then you're going to have high voltage here. So you have to insulate both legs of the split backstay, and you have to be 3 feet from the mast up here. 7 feet off the deck here. There's no reason to put this thing coming down here. That's probably going to change the transmit characteristic. So put this guy as close as you can here. So what I do on these is I take and I a lot of times the sailboat owner will know the exact length of this backstay, and if he doesn't, you can measure it, or you can remove it and measure it. But the thing, what I like to do is I like to find out the length of this backstay, and rather than taking the existing backstay off the boat and crimping these insulators into it, remember this is a serious swaging crimp job here. This cable takes a lot of torque, so the insulators have to be really strong. So what I do is I figure out what the length is, and I go, it's only 5/16 or 3/8 stainless cable. Yeah, it's expensive as hell, but so what? And then here you got ends that have got to be swaged onto this thing to hook it to the boat. So I go and tell them, buy a whole new backstay. So your boat's still in the water, it's still holding, you know, everything's fine. Because if you take this stuff off, the thing off, and go try to cut it and put insulators in it and put it back on, if you're lucky, you'll keep it the same length and close enough that you can adjust the thing and tension it. But in the meantime, the wind's going to come and blow the mast over, and so you either have to step the mast completely, or what you can do though on a calm day is you can have a whole new backstay made with the insulators, and then go and take the old one off and right away put the new one on. And, you know, I'm talking about using a man lift and proper OSHA procedures, but that would be a kind of a shortcut. I think the proper way to do that is to step the mast and then just replace the backstay and put it back up. So the major considerations for the installation: if you got a metal hull, you are home free. If you got a fiberglass hull, you got to create that counterpoise. If you got a metal hull, you just hook the ground from your antenna tuner straight to the hull, and the hull is the counterpoise. You cannot get too much counterpoise. The more, the better. And then salt water is much more conductive than fresh water. So single sideband radios work about twice as good in salt water as they do in fresh water. I'm in fresh water, so believe me, people tell me all the time that single sideband radios do not work in fresh water. That's not true. They just have to be installed perfectly, and there hardly ever are installed perfectly. But in fresh water, everything matters. In salt water, you can get away with a couple of errors and the thing will still function. But in fresh water, everything has to be just so. And they do work in fresh water, just not quite as good, but they do work. So 4-inch copper strap, no more than 3 feet from the tuner. That's rarely able, again, everything's a compromise. Getting that tuner 3 feet from the ground plane is really kind of tough, but using 4-inch strap, you'll be okay regardless. And you can either have a capacitive connection or a physical connection. If you put your ground plane in the water, it's going to have a physical connection to the water. If you put it inside the hull, it'll still work. It'll capacitively couple to the water. So that's kind of a fun fact. The counterpoise does not have to be in physical contact to the water. It can capacitively couple and use the water as a ground plane anyway.
I've got a quick question real quick.
Yeah.
So on the single sideband radio, you said the antenna and the ground plane is all one piece. So on a metal hull boat, would the ground plane not conduct the electricity is the same as the antenna, or have an RF burn or anything?
That is correct. You will still get RF current flowing that way, but then you can think of it as bouncing off the water or bouncing off the hull. So it will use as much of that hull as it needs to make it to do its RF current thing, and then it doesn't go any further than that. So it doesn't electrify the entire hull, but it does electrify part of it with RF energy.
So is there any potential hazard?
No.
On a metal hull?
Not at all. No, sir. Because the metal hull's got such good contact to the water, there's no chance of it ever getting voltage.
I got you.
So I've got a comment here. Haven't done these in a while. Well, I've only done about maybe half a dozen or 8 of them in my entire 35-year career, so I'm no expert at them, but I have done them. And then I have this, it says, is the KISS ground still good? What's a KISS ground? Can you elaborate on that, Bill? Is the KISS ground still good? I don't know what that means. Bill, I see you're unmuted, but I'm not hearing you. You there, Bill? I'm going to mute you and unmute you again, see if that fixes it. Mute, unmute Bill. Bill, do you read me? Do you read me? Over. Bill does not have any volume. Well, then type in the question pool what you mean by, is the KISS ground still good? Have you got audio, Bill? Oh, maybe he's having a sound problem. Hope not. We'll give him a minute to try to recover. In fact, you know what? We're at break time anyway. We should really finish the single sideband section. Let's finish it before lunch here. So you got no volume. I tried muting and unmuting you, Bill. Hopefully you can hear me. If not, you need to log off and log back in if you're not even hearing me. So I'm going to type him a message. All right. So the ground plane acts as a reflector for RF energy. Oh, okay. So what? Thank you. Bill has answered me. Well, is a KISS ground Is the KISS ground still good? I don't think the KISS ground was ever good, but maybe I've seen it. I've never used one. I've never actually used a radio installed that way, and I've never installed one, so I can't say. But let's just say this about that. Radio geeks all have their own opinion. You know, ham radio operators, I don't know if you guys know any of them, but they're like radio geeks, right? And I'm kind of a radio geek myself. So don't take that as an insult if there's any ham operators in the room. But the thing is, they have all these different theories about ways stuff works. So they try something in their Radio Shack. Believe it or not, that's where Radio Shack came from. There used to be a shack at the base of the tower where the guy sat and ran the radio. And there still is a shack at the base of the tower where those cell towers. Go look, that's where all the equipment is. So the guy in the Radio Shack does something like he puts a copper strap between two things, or he does something weird, pounds a copper spike into the ground, or puts a capacitor between 2 points on his radio, and it works. And he says, oh, this is the way you should do it. It works. And then he goes and he makes a widget, and he says, this widget works. I proved it. And he sells the widget, and everyone says, oh, that guy's so smart. Look how good he is. I'm going to buy that widget. And they try it. It doesn't work in their application because the widget was only good at his Radio Shack because of I don't know, the copper content of the soil in that location, or the wiring characteristic of the building, or what the walls were made out of. I don't know why it worked at his place and it doesn't work anywhere else, but that's the kind of thing you have in the radio business. You have all these newfangled solutions that don't work. Yeah, we're going to get to the tuner here directly. So someone just reminded me that the antenna tuner cannot be mounted inside a metal hull. And that is definitely a question in the question pool, and that's going to be covered in an upcoming slide. So thank you for pointing that out. And where do you install the single sideband antenna unit? Two questions in a row on the antenna tuner. It goes at the back of the boat below the backstay. You want it directly below the antenna if possible. And you want to keep that high voltage wire as short as possible. So directly below the antenna. Like for instance, that 10-meter freestanding antenna I put on that 185-foot Coast Guard cutter, I mounted the antenna tuner outside on the rails right next to the bottom of the antenna with like a little 2-foot piece of high voltage wire coming across, and the ground went straight to the hull right there. So it's easy peasy for as far as an installation, but so the antenna tuner ideally is directly below the antenna, and the counterpoise is directly below the antenna, the tuner. So very rare to be able to actually accomplish that. So you just have to understand that that's the optimum place. And then as you make a compromise, you understand how it works. You can make the correct compromise. And then when it doesn't work, you can understand how to modify your compromise, and then you can make it work. So we talk about, again, with models, remember we talk about these things with models because we can't, with our puny human brains, we cannot understand some of this stuff. So like for instance, when we talk about electricity, we talk about water flowing through a pipe, even though electricity is not water flowing through a pipe, but we can understand it that way. So the way we can understand a ground plane is that it's a trampoline for the radio waves. So the radio wave comes out of the antenna, bounces off the trampoline, and goes out to the rest of the earth. So it does make up a quarter wave of the antenna. So between that quarter wave and the quarter wave up above, you got a half wave antenna. The antenna tuner makes it look like that to it anyway. But anyway, this is a quarter wave of the antenna, and it's not necessarily connected to Earth. So sometimes the counterpoise is in the hard top. It doesn't even have to be in the vicinity of the water. It's a trampoline. So the counterpoise is a substitute for Earth. So for instance, this picture right here, this is the counterpoise, all this copper screening all up through the hard top. They took the headliner off, they put copper mesh in there, they hooked a copper strap up to our antenna tuner, presumably is right up here. So the antenna tuner is directly above the counterpoise, and then hopefully the antenna itself directly above that tuner. So the tuner could be anywhere around all around this counterpoise. We want to keep this strap as short as possible, but so that's why I say it's probably here. But so that's an example of a counterpoise. It's not hooked to the water. It still acts as a trampoline for the radio waves to bounce off of. So here's a counterpoise. Note that it goes to the tuner. This is just a grounding drawing. So we don't even have the control wire or the coax going between the radio and the tuner. All we're showing is the grounding. So the ground from the wing nut of this radio, this is the transceiver unit with the microphone on it, or the ICOM's got the separate box with the control. But anyway, this is the where the coax comes out of and goes to the antenna. It goes to the tuner. And then here is our connection to RF ground. This is the wing nut. This is the RF ground plate, all the stuff in the water, the bonding system, right? So this guy, RF ground, goes down. In this case, it's drawn improperly and showing it hooked to the ground, common grounding point. It should actually be hooked to here. So anyway, it's got an RF ground. It's got a connection to RF ground, as do all the other electronics on the boat, right? Your radar display, your chart plotter display, your autopilot, even your VHF radios hopefully have a connection to RF ground. And this single sideband radio also has that. Not the tuner though. The tuner is only hooked to the counterpoise. And of course to the coax and control wire. And there's our DC negative supplies. So this is kind of a, here's our DC negative, our RF ground. They're using the common grounding point as an RF. This is the RF ground over here. This is where the wing nuts should be hooked up. Other than that, it looks right. This would work. There's nothing wrong. You can call this common ground / RF ground. It's done like this on boats all the time. It's just we like to make our drawings show everything discrete so that you understand that common grounding point. Anyone have a question about this grounding and the common grounding point? In reality, is the counterpoise is also the hull, so is the RF ground plate. Well, the RF ground plate is being used on a fiberglass boat. So the hull on a fiberglass boat is not conductive. So I'm not sure what the point you're trying to make there with that statement, but yes, the hull is the counterpoise on a metal boat. When you're using the ground plate, it looks like the hull to the radio, but don't forget the one with the screen and the hardtop. It doesn't have to be ground. All it's got to be is a plate. This guy. So any other questions about grounding around single sideband radios? You know, we need an RF ground to the transceiver, but not the tuner. We need a counterpoise to the tuner with 4-inch strap and a minimum 100 square feet or equivalent, because the dynaplate says 100 square feet equivalent. And then all this other grounding stuff down here is all this other grounding stuff down here is covered in NEI, and the drawing in NEI is actually much better. So there's that counterpoise in the hardtop. The other thing you'll find for counterpoise is sometimes boat manufacturers will glass copper strap into the hull itself. So the copper strap in this case is shown by the yellow in this drawing. This is a drawing for a counterpoise that's put into a Westport yacht. Westport is out on the West Coast. They make 20, 30, and 40 meter super yachts. And this just shows the grid pattern that they're using during their manufacturing process to put in the single sideband counterpoise. And this is inside the fiberglass of the hull itself. And you'll see this on a Beneteau sailboat, at least above a certain size. When the boat comes brand new, it's got a counterpoise glass into its hull. If you got that, or you got a steel hull, you're a happy camper, because doing the counterpoise is the hardest part of the job. And so if it's already done for you, then you can jump for joy. So here's where the only difference between this drawing and this drawing is here the counterpoise is in the hard top. That's the one that we showed the picture of right there. That's this one, is that one. And then this drawing, as you see, now the counterpoise is in the water. So that puts our tuner down by the water. Remember, we want this to be within 3 feet of the ground plane. We want this to be within 3 feet of here with our, wait, let me get this right. The single sideband, the ground strap should be 3 feet to the RF ground. This should be located physically below the tuner, and the antenna should be located physically above the tuner. The antenna is not shown in this drawing. So anyway, this is just the way it goes. We still have a ground for RF ground. Again, this is the same exact drawing. The only difference is we move the antenna tuner down into the bilge because we have to put it close by the RF ground, which is in the bilge. I'm sorry, I called it an RF ground. It's a counterpoise. Yes, sir. Did you have something to say, Ian?
Yes.
Okay.
The RF ground is not the DC is not somehow connected to the DC common ground. Then
it is. It is right here using the common grounding point. See this connection right here, common grounding point to DC negative? That is a single conductor. We don't use all one terminal strip and put all these things on one, because then we create a bunch of ground loops. So instead we have a separate and discrete DC common or DC negative bus, and then we have a single conductor that clamps it to the common grounding point, which also, by the way, this common grounding point also gets the bonding system comes to that common grounding point, and AC safety ground comes there too. So there's 3 different wires that get hooked up to that: the bonding system, the DC negative, and the AC safety ground also goes to the common grounding point. If the day 1 of this class, Ian, we covered this in detail and talked about how this common grounding point and why it's there. The purpose of it is to clamp the voltage potential of all the grounds together so that there's not a slight difference in potential, which, as you know, would cause stray current corrosion. So that's the reason for this. That's the reason for this common grounding point, is to clamp that voltage. And so in answer to your question, yes, these are hooked together. But this one, as I'm pointing out, is not. This is not part of, this is not a ground. This is a counterpoise. How big does the RF ground plate have to be? 100 square feet. So the dynaplate, which is 6 inches by 12 inches, is 100 square feet equivalent. If I were to do another single sideband, which I quite likely will before I drop dead, the last couple I've done, I put in 2 dynaplates, right? You know, one right next to each other, just either side of the keel there. And that way I've got you cannot have too much counterpoise, but it must be a minimum of 100 square feet. I think here's another thing. I think the counterpoise is being labeled RF ground is confusing some. Yes, on this drawing that we're looking at now, this is an incorrect label. This is the single sideband counterpoise. Over here, the strainer seacock, this is our RF ground, okay? The strainer seacock and maybe a grounding plate over here for your electronics, that's fine. This is not an RF ground. This is a counterpoise. So that's an error. Please do not be confused by that. Thank you for pointing that out, Seth. Why wouldn't you connect it to RF ground as well? Well, let's just say that most single sidebands are installed improperly, and they do that. In fact, there are books written out there on this subject that tell you to hook it to the RF ground. If you do that, and then you end up talking on your radio quite a bit, you're going to look outside your boat and all your rails are going to be blue. So you really don't want to crank RF energy all through everything that's hooked to the ground, to the RF ground. And not only that, if somebody's grabbing that rail while you're transmitting, he may very well get an RF burn. So don't do it. It must be separate. It should not be hooked up to RF ground. It seems logical. Why wouldn't you just do that? Because it gives you more surface area, right? You can't have too much. You know, you're cranking your fuel tanks, you know, your fuel tanks are going to turn blue too because they're metal and they're bonded. So you really don't want to do that. So don't hook the RF ground to the single sideband tuner. That's got to have its own separate, standalone, isolated from all others, counterpoise grounding plate. Aluminum boats are a special case because we're using copper strap. So obviously for RF ground, on a metal boat, you don't have RF ground. Everything just gets grounded to the hull. So that's all this is saying right here. But in order to hook a copper strap to the coupler, from the coupler to the hull, you're going to want to use a capacitive coupling, anti-corrosive grease, because copper and aluminum don't play well together. So this capacitive coupler thing allows you to hook, it's just a little stud thing, and you hook the copper on this stud, and then you hook the hull on the other stud, and that couples the two together without the problem of galvanic corrosion. And here's the thing that someone reminded me of a little while ago. The antenna coupler must be outside of metal enclosures. Remember, the antenna coupler, the high voltage wire, the ground strap, and the counterpoise are all part of the antenna. So if you put that antenna tuner inside a metal box or inside a metal hull, you just put part of the antenna inside the metal box. And that is not a good idea. So there's a test question on this too. The antenna tuner or coupler must be outside, not in a metal box, outside metal enclosures. So the counterpoise, how big does it have to be? Minimum of 100 square feet, or the hull, or mesh screening. If you're using mesh screening, you literally need 100 square feet of it. It's really easy to not have enough, but you can't have too much. So 4-inch copper strap is our tool of choice for, or a conductor of choice for hooking up this counterpoise to the coupler. We really want a lot of surface area. If you do this with 8-gauge wire or 1-inch copper strap or something like that, you will see a decrease in performance because of that. So you really want to go to 2-inch, 4-inch, really we say 4-inch copper strap. I see it done with 2 a lot, and they do work. And then you no more than 3 feet to the coupler. This gets fudged as close as possible to the coupler because 3 feet is like an impossible to meet spec. At least the boats I work on. I mean, I could be mistaken, but hey. So that's, you know, on non-metallic hulls, we have to create the counterpoise either using screening or using a dynaplate, or using that strapping back and forth installed in the hull. So some people do that. They'll take copper strap and just epoxy it inside the hull, back and forth, back and forth, back and forth, and they use that for a counterpoise. If you're going to do that, you use the same spacing between the strapping as you have of the strapping. So if you're using 2-inch copper strap to go back and forth, you go up one way, leave a 2-inch gap, come back this way, 2-inch gap, come back that way, 2-inch gap, or a 4-inch, you leave a 4-inch gap. So that it actually looks like a solid piece of copper sheet when you do that to the radio. So after you get out to 100 square feet, you can quit gluing strap on the inside of your boat. That's what a dynaplate looks like when it's installed, 6 by 18 inches. Like I said, I would put a second one over here and strap them together just so I have a really good counterpoise. And So you have to put this is a pain in the butt, and there's a bronze bolt that comes inside. There's 4 bronze bolts that come inside, and one of those bronze bolts you hook up your copper strap to, and just use the largest dynaplate that you could fit. Obviously, this guy could have fit a bigger one, but watch out for this too, because the hull is curved and the dynaplate is flat. So you can't have 1/4-inch gaps under here. If you have to create a fairing spot for that with fiberglass, that's what you're going to have to do. You can't just leave because this hull is curved and this plate is flat. So you can't just like have a 1-inch gap here and it's touching down here and just fill that with caulk. That would be a very bad idea. So once it's all installed and then you think it's good, do a voice radio check. There's a thing called WLO down in Mobile, Alabama. I think they're still in business, although the old guy that was doing it died, but they still were in business. And you can find them on the single sideband test service on the internet. And Google it up, and you can make a voice radio call to them. You call them up on the 800 number and you say, hey, I want to check my radio. I'm in Chicago. They say, okay, go to 14.1 meg and give me a minute. I'm going to aim my antenna. And so then you hang up and you call them on 14.1 and they come back and say, yeah, you're sounding good, or you're all broken up. It's really weak. You better do something right. So you could do a voice radio check to one of these single sideband ones. You could do your DSC auto test. Send an auto test message to the Coast Guard station for DSC, and then your RF power test, we're going to go through that. And so the SWR can only be measured when there's power coming out of the radio, which means you either have to whistle or scream into that microphone, or there's something called frequency shift keying, which is how you send Morse code, and I'll go through that in a minute. And so depending on what time of day, of course, you need to know how to use a single sideband radio to run an auto check to the Coast Guard station. And remember, the auto check is only available on 4 meg. So if you can't hit a Coast Guard station with 4 meg, you can't do a DSC auto reply test. So the RF and power test is like this. We want at least 120 watts forward and no more than 5 watts reflected. And we're going to be monitoring our voltage during the test to make sure that the voltage is not sacking out, huh? And so watch out. Some single sidebands come out of Europe, put out 250 watts. And so there's different wattages of single sidebands. In this country, they're supposed to be 150 watts if they're going to get FCC type approved. So here we have the drawing set up for what we're going to do when we're testing our single sideband. Again, you're supposed to put it into a dummy load first to make sure everything's cool before you hook the antenna. So we put it to our dummy load. We've got our slug in here. This is our 2 to 30 megahertz or 2 to 50 megahertz slug, whatever kind of slug it is. We aim it at the antenna and we're measuring our forward power. So if you're trying to do this using voice, you're going to have to scream into that freaking microphone as loud as you can to get this thing to pump all the way up to 150 watts. Or there's something called frequency shift keying. So remember I said we run in USB upper sideband mode. So there's lower sideband mode, there's AM mode, FM mode, and there's frequency shift keying. I refer to the modes of an ICOM 802, the most common single sideband radio on the market. And so you would put it in frequency shift keying. And frequency shift keying, you squeeze the mic, that's a 1 or a dot, or I don't know. It puts out all 150 watts of just carrier, no modulation, when you squeeze the mic, and when you let go, it goes away. So if you put it in frequency shift key mode, then you are able to use this watt meter more like you use it with your VHF radio, where you just squeeze the mic, read the power, unsqueeze the mic, reverse the slug, face it back that way, squeeze the mic, and measure the reflected power. So you aim the thing towards the antenna, measure the forward power, aim it back towards the radio, you measure the reflected power. And again, we want about, what am I doing here? Let me get back to where I wanted to be. We want at least 120 watts forward and no more than 5 watts reflected. And note also that we are measuring the voltage here and monitoring the voltage while we squeeze the microphone on frequency shift key. So it's putting out full power, and we see if we don't get an unacceptable voltage drop. The specs for those voltage drop are right here. Leave 1 volt basically, 2 volts on 24. Remember, once this thing's installed, this coax is going to be maximum 2 dB loss. So now we took the dummy load off of the thing and we hooked it up to our antenna coupler and our antenna. And these are RF ammeters. I don't own an RF ammeter. I've never seen an RF ammeter. I'm sure they exist. So what this is saying is you key the microphone and you confirm that you have just as much current flowing through your ground strap as you do through your high voltage wire. If those two are exactly equal, then your radio is installed perfect. You know, typically you'll get a slightly less here because this thing is slightly insufficient, and so you'll get slightly more current here and slightly less here. But ideally, they would be exactly equal. Here we're still monitoring the voltage while we're doing our transmit, and then if you're doing this with voice, you're going to want to scream into the microphone so you get full power. This is not unlike doing a VHF radio test. You're using the Bird watt meter. You're just using a different slug. Remember, this slug, it's got a frequency and power associated with it. So you need the 200 watt or 150 watt slug rated for the frequencies that we're using, which is 2 to 30 megahertz. So you're going to get a 2 to 50 megahertz slug, something like that. On the VHF, we use 100 to 250 meg because we're working with 156 meg on VHF. So this one's got to be rated for the frequency for single sideband and have the power capability. These Bird watt meters, if you don't already own one, you can find them on eBay fairly cheap, a couple $100, maybe as cheap as $100. But make sure you get the right slug, because if you have to buy this slug new, that's going to cost you $100 all by itself. So when you buy this thing, if you can get the one that already has if you're buying it on eBay, look for one that's already got the single sideband slug and the VHF slug. And you as a marine technician don't really care about the other slugs for testing business band radio and all that kind of stuff. You just want the ones for single sideband and VHF. Two different slugs, 1 meter. Any questions so far on single sideband? This is a tough one. The first one of these you do, you will struggle. So find a guru to help you. You must have a ship's radio license, and you must have a VHF radio, which also means with DSC capability, and that also means you have an MMSI number, because you wouldn't get this stuff. You have to have an MMSI number. It really should say and MMSI number on this bullet up here. So all these radios have DSC, so you have to give it a GPS signal. You have to give it an MMSI number. And so then, you have to make sure it's working. So you have 2 antenna connections back there. Remember, one's for the transmit receive antenna, and one is for the DSC watch antenna. And so the watch antenna is a receive only antenna. And there is a thing called WWV, which is a timing pulse. And it comes out at the top of each hour, a long pulse, and then every 5 seconds, beep, every 5 seconds, beep. And so it comes out of Boulder, Colorado from the Bureau of Standards. And these are the frequencies it comes out on. So you can tune into one of these frequencies and listen for the beep. If it's getting the beep, then your receiver's working. That's one way to get those, you get these time ticks from the, this is how cell phones are timed, by the way. They pick up this pulse, and that's how they all have the exact same time. And this time is synchronized to the nuclear clock as they watch a cesium atom decay and time it. I don't know. The nuclear clock works somehow, but they're super accurate. And so this is how you can check the receiver. The receive antenna, you just tune in one of these frequencies and see if it's receiving. Now, to check the DSC antenna, remove the transmit receive antenna from its jack on the back of the radio, and remove the DSC general coverage from the radio. Install the DSC one onto the transmit receive jack. So what you've just done is you put the DSC watch antenna onto the transmit part of the single sideband radio. So do not squeeze the microphone now, please, because it's a receive only antenna. And then, because the DSC, you can't do the WWV test using the DSC watch receiver. It's only watching for DSC frequencies. So you have to put it in here and then tune the radio to 2.5 or 5 meg, and then you should hear the WV beeps coming in. So what you're doing is you're moving the receive antenna to the transmit jack and then using it to receive the WWV signals. And then put them both back the way they were. And do not squeeze the microphone into the DSC watch antenna. You will damage it instantly. It won't take very long. And so then put it back the way it was and then perform an automated test. Here's your MMSI number for doing the automated test, right? And the frequency that you use is that 4.2 megahertz. It's listed in that DSC section. You do a call type test to this MMSI number on that frequency and you get back ACK. So if you can do all of these things, and in addition to, of course, testing forward and reflected power here, we're testing forward and reflected power, right? And then we also test our DSC watch antenna here.